We are going to kick off AI Day here at Driven 2020 with Tom Wilger, our head of artificial intelligence.
Hi there. So great to meet with everybody virtually. So I'm Tom Wilger, as Krista said. I've been with BP3 for about 5 years, and I head up our artificial intelligence practice. And, you know, in my role at BP3 over the last few years, it's interesting because I've been to a lot of AI conferences. And I'd say for the most part, each one has had some pretty interesting talks. But the funny thing is I always come away from them asking, how do I apply what I've learned here to help our customers solve their problems? And most of the use cases that were presented at these conferences were really cool. But they were also very specific. And for the most part, these companies had to spend probably millions of dollars developing them and the solutions. And the brutal fact is that for most businesses, that there really aren't a whole lot of AI problems out there that can justify that kind of effort and spend. So today, we're not going to talk about what I call Moonshot AI use cases. And although I think that they're really cool topics, we're not going to talk about autonomous vehicles. We're not going to talk about curing cancer. And we're not going to talk about creepy robots walking around taking over the world. Instead, I want to talk today about how we apply AI problems that our customers run across on a daily basis. And so we're going to talk about maybe sort of the opposite of that is really what I'd like to call walking across the street AI. And today we're going to talk about understanding customer intent using text classification and something called named entity recognition. I'd like to talk about intelligent document processing and how it's different depending upon whether you're dealing with structured, semi-structured, or unstructured documents. But we're also going to talk about how we use AI for really more specifically with expert systems in healthcare for building patient treatment protocols. And what I'm hoping that you'll come away with at the end of the day is a better understanding of where AI fits in and can provide real value in solving day-to-day problems that we're all dealing with. So let's sort of set the groundwork. So AI is one of those fields that, because it's been moving so quickly, there's a lot of confusion in the marketplace about what AI is and what it can do for us. And if you ask 5 analysts to define AI, you're probably going to get at least 5 different answers, maybe even more. But the most helpful one that I've actually been, when I look out all the analysts that are talking about it, is one from Gartner. And they define AI as applying advanced analysis and logic-based techniques, including machine learning, to interpret events, support and automate decisions, and take action. And at BP3, we really think of AI as a discipline of making our solutions more intelligent by applying such techniques as machine learning, rule-based inferencing, and even mathematical optimization. So besides just being really cool stuff, what's the big idea with AI? What's the big deal, and why is everyone clamoring to get on board? Well, the companies that we've worked with that seem to be moving the needle the most when it comes to applying AI to their businesses seem to be looking at it from really 3 different perspectives. The first is really around optimizing costs. And this can be anything from helping people do their jobs faster and more efficiently to getting higher returns on their capital investments through something maybe like quantitative finance. The second is improving their existing business by making decisions faster and with more consistency, and improving the customer's overall experience through techniques like product recommendation and maybe even next best action. And then finally, some companies are using AI to create whole new lines of business, like collecting and organizing data as an asset, or training and selling the use of predictive models that maybe help other companies save and make money. But what I'd say in general is that the reason that most of our clients are interested in artificial intelligence is the impact that it can have on improving automation. So why is that? Well, our clients' businesses are under incredible pressure to be more efficient, either as a response to competition or in order to allow them to grow and satisfy the market demand. Our clients want more automation because it's the single most effective way to reduce cost while increasing the speed to address those pressures. And there's some great tools available out there to automate. There's RPA tools like Automation Anywhere and UiPath. There's workflow tools that you'll hear about actually in some of the days coming up here during our conference that are both proprietary tools and open source tools from companies like IBM and Camunda and even Red Hat. Even with all these options, though, those tools for most automation are actually inadequate to the task. Let me walk you through an example real quickly to kind of illustrate, at least from our perspective, how frustrating this can be. So let's take a look at a basic invoice intake process. Now, processing invoices is usually divided into 3 different segments. There's an intake process where the invoice is entered into the system. There's usually an approval process, hopefully. And then there's a payment process. So of these 3, the intake process typically takes up about 75% of the total effort. And this process, this intake process is pretty much something that every company has to do. It's tedious, it's time consuming. And so from our perspective, it actually sounds like a pretty good place for automation. So let's kind of go through it. So invoices typically come as either email attachments or sometimes a snail mail, where they have to get sorted and scanned and turned into PDFs. Now, large organizations typically outsource their mailroom operations, including the document scanning. And fortunately, for all of us, paper invoices are slowly going away. The email attachment extraction is actually pretty straightforward and can easily be automated using something like robotic RPA or robotic process automation. And in either case, though, you eventually end up with a PDF document for the invoice. So at this point, the real work begins. And we do this by extracting the data from that invoice. And this includes information like the vendor, the date, the PO number, if it exists, and all of the line items and the amounts that are on the invoice. We can automate this task using intelligent document processing software, and we're going to talk a little bit about that later on today as well. Okay, so far we've done a pretty good job of automating the invoice intake process, so not a lot of frustration there. And in fact, once we have all the accounting transaction line items, we can even use RPA to enter that accounting transaction into our accounts payable system. But here's the rub. So now we have to actually convert the line items that were on that invoice and the amounts to the appropriate accounting transaction line items. And now, if you were able to stay awake in accounting class, which I was fortunately able to do the second time around, you'll remember that non-PO invoice accounts payable journal entries have a credit to the accounts payable GL account for the total amount of the invoice, and 1 or more debit entries corresponding to the expense GL accounts against which those invoice line items are charged. So it's the job of the accounts payable clerk to be able to read and understand the line items on that invoice and match them up to the appropriate GL expense account. So going back to our automation, this reading and understanding of the invoice line items and then matching them up to the appropriate GL expense account is a task that we cannot achieve with purely mechanical automation tools like RPA or workflow. So this task requires understanding and thought and is actually what we refer to as a cognitive activity. The good news, though, is that we can automate many of these cognitive activities using artificial intelligence. And in this particular case, named entity recognition, which we'll be talking about later in the day. So our customers are interested in artificial intelligence because it allows them to automate these time-consuming and expensive processes that can't be automated with mechanical automation tools alone. It's this combination of automating the mechanical and the cognitive activities together that is called intelligent automation. I want to introduce Chris Rennie. Chris, worked with Chris for it seems like a very long time. We're good friends, and he's going to talk today about intelligent document processing and some interesting AI that's around that.
All right, well, thank you, Tom. So I'm going to be discussing intelligent document processing. So first, let's define intelligent document processing, and we also call it IDP. So IDP are software solutions that blend the power of AI technologies such as OCR, which is optical character recognition, or named entity recognizers, NERs, machine learning, and we efficiently process all types of documents, extract the relevant information, and then feed the output into downstream applications. So that's kind of the definition of intelligent document processing, or IDP. Currently on the market, there's a lot of different packages that do this. There's FlexiCapture from a company called Abby. IBM has a product called DataCap. Automation Anywhere has IQBot. UiPath has Document Understanding, and there's many, many more. All of these software products have similar capabilities. Some are easier to work with than others, but in general, they all work the same way. They all require some type of setup to make them work correctly. And this setup can vary significantly depending on the type of data you're extracting, the types of documents you're dealing with, and the confidence level that you need in that data extraction. For this presentation, I'll go through the different types of document structures that we see and give you a feel for how we extract data from those structures and where AI fits into that. The simplest type of document that we see, at least from a data extraction perspective, is called structured documents. From these documents, we need to extract printed or handwritten or even checkbox values. But everything in a structured document is either at an absolute location on the page or at some relative offset to a known anchor point, like a label. Common examples of structured documents that we see are tax forms, or pretty much any kind of government document, licenses, passports, and even handwritten applications where the boxes are defined and you put a letter in each box. What sets a structured document apart from the others is that you always expect that a value, like last name in this case, will always fall within some distance away from an anchor point and will be contained within a certain amount of space within that document. To extract data from structured documents, we typically use something called a positional data extractor. At its simplest interpretation, we configure this extractor by locating and defining the anchor points and values. In this example, the anchor point for the phone number is the label outlined in red that says primary phone. Based on the location of this anchor point, we can define where the value for that phone number will be located. When a positional data extractor sees characters in the primary's phone values bounding box, which is marked in blue here, it can assign those characters to the phone number data element. So it's matching the anchor and the value. The next classification of documents that we see are called semi-structured documents. You can think of these as reports where all the data is in a standard order, but because each section may vary in length or even break across pages, we can't really predict where something will be on the page or even what page it's going to be on. A common example of structured documents that we work with are patient medical records. Sometimes you might use a positional data extractor to pull out some of these fields as long as you can find a good anchor point. and you can predict the size of the value box. But you have to be careful here because, like in this case, if the value of constitutional symptoms happen to wrap to the next line, a positional data extractor wouldn't be the best choice for that. A more common approach here would be the use of what's called a form or key value data extractor. This extractor uses machine learning model, and it's been trained to recognize the relationship between the keys and values within a text document. They work well, they're easy to configure, but they're not foolproof, so they sometimes miss data elements. So if you use a positional extractor, you might get better results overall. It could be also that you need a larger training set for the machine learning model. There are also extractors called table extractors, which are similar to form extractors, but they pull data out of tables. A good example of this would be items on an invoice. These extractors are based on machine learning models also, but instead of being trained on key value pairs, they're trained on tabular data. Finally, there are unstructured documents. With this kind of text, the only assumption we may be able to make is the language of the words, hopefully some kind of grammatical structure of the language, and sometimes the domain of the document. So in this case, we're looking at another part of the patient's medical record called a history of present illness. This is a textual description of what's going on with the patient, and usually has embedded with it symbols, diagnosis, and in some cases even negative symptoms. To extract this type of data, we use an extractor that's built in what's called a named entity recognizer, or an NER. NERs are another type of machine learning model that are trained on a large text corpus to recognize specific types of terms or entities. Common NERs that you might find are trained to recognize people's names, places, dates, companies, and even currency values. The one we use for this extractor is trained to recognize medical language. You'll probably notice as we've gone through these different classifications of documents that some documents, like a patient's medical record, may contain structured, semi-structured, and also unstructured sections. Being able to identify these different classifications and then choosing and configuring the best extractor is ultimately what's needed to get the most accurate extraction results. As I said earlier, there are quite a few software products out there that do intelligent document processing. Our consultants at BP3 work with a lot of them. Under the hood, they follow a similar process and they have similar components. And here's a representation of these components, and I'll go through them in more detail. The extraction process begins when a document lands in some storage location, like a directory. And then most IDPs will pass the document through an optical character recognition engine, and that's an OCR. OCR are machine vision algorithms that have been trained to recognize characters. Depending on the engine, it might have been trained on different fonts, character sets, handwritten text, or even barcodes. Once the characters are identified, that OCR engine groups those characters together into nested sets or blocks. These blocks can be words, lines, even paragraphs. The information in the blocks not only contain the identified characters, but also the location of those characters on the page. Once the OCR is complete, these blocks are sent to the various data extractors that have been configured for that document and document type. And the data extractors pull out the specific data elements that are set up in the domain of values that need to be extracted. And then the next step is aggregation and validation. So you might be asking at this point, why do we need to aggregate this data? Well, the data extractors might have found multiple instances of the same data element, and so we need to figure out what to do with them. For instance, two extractors might have found two instances of a patient's name. So we know at the end of the day, we only want one patient name. So the aggregator will select the instance with the highest confidence level. This is different than, say, the symptoms that we might be extracting, where there could be many of them, and we want to return all of them that have a confidence level that's above some predefined threshold. And this confidence level occurs at multiple levels. The OCR is done with a confidence level that represents how confident the OCR engine was in recognizing something as text. And the extractors have their own confidence level, which represents that the correct value was extracted. In some cases, the extractors won't find all the values that they're looking for. Maybe the confidence levels for an OCR character or extraction fell below some predetermined level. In this case, the system needs a human to look at the document and validate and correct the data. And this is done in what's called a human loop, which is shown at the end here. A human loop is really just a UI where the user is shown a document and is able to validate the results or make corrections. In either case, once the processing is complete, the structured data from the document is stored so that it can be used for automation and downstream applications. BP3 consultants work with a lot of these IDP products. One of our favorites, though, is one that we built using Amazon Web Services or AWS. Apart from its scalability, one of the things that we like most about it is that we can extend the basic AWS data extraction capabilities to include functionality that's specific to our customers' automation needs. Using this framework, our consultants are able to configure and deploy robust document processing pipelines that we can scale to process hundreds of thousands of documents per day. Now I'm going to take you behind the scenes and walk you through at a very high level what we do to create a data extraction pipeline for a new document. Using our framework, the process our consultants follow is pretty straightforward. The process starts by the consultant defining the domain of data that needs to be extracted. Typically, she's working with the client to figure out what's important in the document from an automation standpoint and how that data might relate to other data elements that are being extracted. Next, based on those data elements and the types of documents, the three types of documents that each document can contain, she selects and configures the appropriate data extractors. And then finally, for basic documents, the consultant deploys the document processing pipeline to AWS. And for more advanced documents that may have some anomalies or maybe data elements that reside in some domain-specific unstructured text, the consultant may need to create a custom extractor, which is typically written in Python, or we might train a machine learning model and create an NER extractor. So to review, intelligent document processing, it's a way to blend AI technologies to efficiently process all types of documents, extract the relevant data from them, and feed the output into downstream applications, typically using automation. And there's a lot of packages out there that do this kind of work. We discussed some of them, but they all follow a similar process and have similar components. And then we also discussed the three basic types of documents: structured, semi-structured, and unstructured, and the AI technologies that might be used to extract the data from those documents. And then lastly, we went through a typical workflow that most IDP use to extract data, including a solution using Amazon Web Services.
Okay, so Chris, now we're going to talk a little bit about natural language processing, natural language understanding, and really in using it for understanding customer intent. So we've been doing a lot of work lately for our clients using RPA to automate repetitive tasks like looking up and sending out a customer's loan statement, or maybe sending out letters of appeal for healthcare providers, and even filling out online state and county sales tax forms. Pretty tedious stuff. But we've been especially busy helping our clients in financial services industries dealing with the economic fallout from COVID-19. And one of our clients is in the auto financing business, and they have been inundated with requests from borrowers to defer payments on their loans. So we built a bot that works through their existing process to their existing system to process these requests to modify a borrower's loan to defer up to, in most cases, 3 payments. And using RPA in this way is great because the robots can basically work their fingers to the bone and chew through all this backlog of the tens of thousands of requests for payment assistance in just a few days. And where this would actually take humans months to go through all of that work. Now, the only problem with this approach is that it requires 2 things. First of all, you need to know that the borrower is actually requesting a payment or requesting payment assistance. And then secondly, you need to know the number of payments that they're really trying to defer. So if the lender receives this information through, say, their website, where the borrower might be able to click on a link, request payment assistance, and then fill out some form, which includes the number of payments that they want to defer, then we'd be good to go. But a lot of financial institutions don't work that way. Instead, they're providing, basically, they provide what's really a self-service website or a self-service portal where the customer can, well, what they can't do is they are not providing a self-service website where the customer is able to, hunt around and find what they're looking for. Instead, what many lenders are doing is they're providing a secure messaging service where the customer can submit their request, and then a human customer service agent reads that message and then responds with the appropriate action. So you can imagine during this pandemic, these tens of thousands of requests for payment assistance are mixed in with requests for other things, like reprints of their loan statement, maybe because they were filing their taxes, or an explanation of why a late payment fee was being charged. And some of these requests can be processed by RPA bots, while others require a human to do the work. So for the ones that we can automate with RPA, the challenge is understanding the language in that request and then invoking the right bot. So now imagine you were working in customer service for, say, an auto lender, and you're responding to customer messages being sent through this secure messaging portal. And also, let's assume that we've created some RPA bots to help you out. We've got one for that automates the request for deferral for a given number of loan payments. And then we have another one that sends out loan statement reprints on request. Now, what you have to do here is really two things. First, we want to be able to leverage these RPA bots to automate the processing of payment deferrals and statement reprints. But then also, we want to teach our robots to understand these customer requests so that it can separate out the requests for automate that basically we can automate from the ones that need to be handled by a human. So what we've done is we're diverting messages from the secure messaging queue and routed them through our robot request router. And the robot request router actually uses artificial intelligence, more specifically natural language processing and machine learning, to classify this unstructured text and extract the relevant pieces of data from the messages. When we begin this process, our robot isn't really smart, but our message labeling team from customer service, which is really just people who have been trained to answer these questions and deal with the responses directly, they're going to actually start teaching the robot to recognize the different types of customer requests, as well as to recognize the parameters needed by the RPA bots to automate those requests. Over time, the robot learns to understand the content of these customer messages more and more, and what's going to end up happening is that more and more of that work will then actually get directed directly to our robots. So let me give you an example. So here's the first message from a customer that goes to our customer service labeling team to process. And this message came from a borrower who is asking to defer 3 payments on their car loan. And the first thing that we're actually going to do is we're going to classify this message. And since this is a request for payment assistance, we're going to select the first option, and then we're going to go ahead and click next. And the other piece of information that we're interested in is the number of payments that they want to defer. And to capture that, we'll highlight the number 3, and then we're going to select requested duration. Now, when we click submit, 2 things are going to happen. Since we've created a bot to automate the payment deferrals, the information from this message will be routed to our robot request router to the payment deferral bot. And that bot then is going to automate the processing of that request. But the other thing that's going to happen is that the training data that we've just created by labeling this message will then be used in the background to start training our machine learning algorithm to recognize similar messages so that it can start doing the work of labeling on its own. All right, here's the next message. This one is a customer is asking for a reprint of their December 2019 loan statement. And we're going to classify this as request statement. And for statement requests, we want to pull out the month and the year for the statement being requested. And to do that, we're going to highlight those pieces of the message and then select the month and the year labels. All right, now things are starting to get interesting. So remember when I said that the training data gets fed back into our machine learning algorithm so that it can start labeling the messages on its own? Well, here's the first time that we start to see the AI getting smarter. This is another message requesting payment assistance. And if you look over on the right, you're going to see a 20% and next to the request payment assistance option. And what that means is that before we are shown this message, the machine learning algorithm already had tried to classify it. And in this case, it was only 20% confident that of the result. So not really good enough for us to let it fly solo, because we've actually set the threshold of that to 65% before we let the algorithm label something on its own. So here, we're going to confirm that this is a request for payment assistance. And now we're going to identify the requested deferral duration. Okay. Now here's a request that we can't automate right now. It's really just too complicated. But that's okay. We're going to classify it as other, and then our router will be able to forward it back to the queue to be processed by a human. All right. Now we're getting somewhere. Our machine learning algorithm has looked at this message and is 67% confident that it's a request for payment assistance. And since this is above that threshold of 65%, it'll automatically just go through the process. But it was only 45% confident it could identify the requested duration. So we need to give it a little bit of help. So as our labeling algorithm gets more and more data, it gets smarter and is able to do more of the labeling work on its own. Once it's trained, occasionally it's going to come across a message that it can't understand. But the customer service labeling team will catch that message because the pre-labeling confidence level of 65% won't have been met. Eventually, over time, though, the labeling algorithm should be able to process even those more difficult messages. So this combination of artificial intelligence and RPA is one of the ways that our clients can evolve from simply automating mechanical activities to incorporating cognitive capabilities that drive them more towards intelligent automation. So if we look at this from what we call a reference architecture for this solution, what we've just looked at is an example of what's called augmented intelligence, and it's actually coupled with machine learning and RPA. And one of the advantages of this approach over some of the other applications of just pure machine learning is that you start getting a return on your investment the day you turn it on. Now, one of the challenges of machine learning by itself is that even when you turn it on, you have to actually power it with a lot of data. And pulling all that data together can take a lot of time and cost a whole lot of money. But the approach that we've used here doesn't actually require that you start off with an initial large training set of data. And instead, you label the data as you go while reducing the overall effort to your internal teams. So certainly the solution will become much better over time, but by using augmented intelligence, you're able to bridge that data gap and have the solution begin paying for itself much sooner.
All right, so I'd like to introduce Tracy Hires. So Tracy has been with BP3 for about 5 years, and I've worked with Tracy for a very long time. And what he's going to talk about today is we do a lot of work in healthcare, and one of the things that we've been doing a fair amount of is automating treatment protocols for patients. And so he's going to walk through an example of that, kind of show you what it looks like.
Hi, so what we're going to talk today about is automating a protocol. Before we do that, I just want to review a slide that Tom showed you earlier. And really what I want to remind you is that when we talk about AI, we can really classify decision automation into three big buckets. Data-driven decisions are useful when we can't articulate the policy or rules used to make a decision, but we have lots of examples of good outcomes. This is machine learning. Policy-driven decisions are those decisions that we have a clear idea about how the decision should be made. The logic to apply it to a specific set of conditions is well known and widely agreed upon. Here we use expert systems or business rules. Finally, there's a third class of decisions, which we're really not going to cover in detail today, but you should know about. Goal-driven decisions or mathematical optimizations are a class of decisions where the goal of what we're trying to achieve is known, but it's not really apparent how to get there. These types of problems often appear in planning, scheduling, and routing. Because healthcare protocols use well-established policies and procedures to intervene when a set of conditions are present in a patient, these types of decisions are classified as policy-based and are well-suited for rules-based inferencing. DMN is a useful technology for implementing these types of decisions, and today I'm going to show you how we might do this to automate an insulin dosing calculation. When we consume carbohydrates, they are processed by the body to produce sugar in our blood. Now, normally the body responds by producing insulin to absorb this sugar and make it useful as fuel. But people living with diabetes do not have the ability to produce enough insulin to absorb all of it. The solution is to inject insulin into the bloodstream when we consume carbohydrates so that the necessary insulin is present when sugar enters the blood. Now, according to the CDC, more than 1.5 million Americans today are living with type 1 diabetes, so there's a pretty good chance that you know someone who is dependent on daily insulin injections. Within the last decade, several products have come on the market that make it easier for folks with type 1 diabetes to manage these injections. But for many of these products to work, they've got to be able to accurately calculate how much insulin a patient needs at a given point in time. Now, the formulas are well known and largely based on a patient's blood sugar level, the amount of insulin on board or insulin currently in the patient's system, and how many grams of carbohydrates the patient is about to consume. So before I go any further, I need to issue an important disclaimer. What I'm about to show you is a simplified example of this calculation, but it is not a substitute for actual medical advice. If you have diabetes, or if you think you may have diabetes, you need to consult a qualified medical professional for help managing your condition. Having gotten that out of the way, let's look at how we might automate this decision using DMN. DMN, or Decision Model and Notation, is a graphical language for expressing the logic required to make a policy-based decision. It's made up of a few simple shapes and arrows, and behind each of the shapes are expressions of either a data structure or a piece of logic. Here is a decision requirements graph, or DRG, for the insulin protocol decision. At the bottom of the graph is an oval labeled patient. This represents the information or input data required to make this decision. Here, the patient contains all the information that is required. The patient has a blood glucose level and a desired carbohydrate intake, a history of dosing, and some parameters about how her body uniquely processes sugars using insulin that must be accounted for when making the decision. You'll notice a couple of arrows going from the patient into two rectangles. The rectangles represent the decisions that we'll make. The arrows represent that a piece of information is required to make that decision. So to decide how much insulin is on board, we need information contained in the patient input data. To determine the required insulin bolus or dose, we need information contained in the patient input data, but we also need to know the result of the insulin on board decision. There are no arrows coming out of the determine insulin bolus decision, and this is the final result of our DRG, and really it's what we care about as we're making this decision. So having gotten that out of the way, let's take a look at the insulin on board decision in detail, shall we? So what we're looking at now is the decision logic within that decision insulin on board, and it's expressed using the friendly enough expression language, or FEEL. Here we're calculating 3 intermediate amounts, and our final result is either 0 if we don't have any insulin on board, or the result of a linear decay function if we do. We assume that it takes 5 hours to process a dose of insulin, no matter how large or small, and the dose gets processed at a constant rate. So if the last dose was administered less than 5 hours ago, the amount of insulin is given as the result of this simple linear function. And if the last dose was administered more than 5 hours ago, then we expect that there is no insulin on board, and we return 0. Astute readers will notice that if more than one dose has been administered in less than 5 hours, our calculation is going to be incorrect. But hopefully you get the idea about what we're trying to accomplish here. All right, so now we're returning to our DRG. We've calculated the insulin on board. We have that patient data, and so now we're ready to recommend an insulin bolus. Let's take a look at that. So the first thing we do here is calculate how much insulin we require to process the sugar currently in our bloodstream, plus the sugar we're about to consume. We'll store that in a calculation I'm calling required insulin. I pulled this formula for this calculation off Wikipedia, so that means that it's 100% accurate. Once I know how much insulin I require, all I have left to do is subtract out the insulin on board. This was the result of the last decision we made, and this is the leftover insulin from the prior doses. And what we're left with is how much insulin is required to dose right now. Note that this number could be negative. That is, if the insulin on board is more than what's required. And if it were negative, that would indicate that the patient is likely to become hypoglycemic, in the near future, unless they take some course of action by really ingesting some kind of carbohydrate. That could be a sugar pill, it could be a piece of bread, whatever. But they'll need to consume some extra carbohydrates. How much they should consume is really a decision itself. It's outside of the scope of what we're trying to accomplish here. But you can see that we could add another decision to the decision graph. We could create an entirely new decision service to calculate that. But it's certainly another automation opportunity. So what you've seen is that insulin dosing is a fairly simple protocol with very few inputs and only a few calculations to make. In fact, it's simple enough that hundreds of thousands of people make this calculation multiple times every day without the aid of any automation. Even simple decisions, when they're made often enough, can benefit from automation though. Automating healthcare protocols like this can improve quality, leading to better outcomes and healthier patients. For enterprises not focused on healthcare, automating repetitive decisions leads to increased consistency, improves transparency for the stakeholders of that decision or the outcomes from that decision, and in the end, frees people up to do more important value-adding work.
Cool. Well, thank you very much, Tracy. I think that's a really interesting example of DMN and policy-based decisions. And appreciate you putting it together.